Okay, so let's start. So we're going to continue talking about multi-arm bandit today, and we're going to talk about a slightly more advanced algorithm that achieves a much faster, regret rate. Right, and the algorithm is also pretty intuitive, and we will see that it actually makes a lot of sense. Okay, so let's just recap the multi-arm bandit, the learning process. Right, so this is an interactive learning process. At every round, the learning algorithm will decide to recommend an arm, right? An index from 1 to capital K. And once you recommend that arm, you're going to pull that arm, and the learner will observe an ID reward that is sampled from that particular arm's distribution, right? So this is unknown distribution. You only get to observe the rewards that corresponding to the arm that you just pulled, right? You don't get to see other information in this round. So this is the learning setting, right? And the learner's job is to actually leverage the information so that gradually it can learn how to pull a very promising arm, meaning the arm that has potentially a very high expected reward, right? And this matched to the learning metric that we designed, right? So we were interested in controlling this regret, which is the difference between the best you could do, right? If you knew the best arm and you pull that best arm for all capital T rounds, right? This is the best expected reward that you could get. Like you can do better than that, right? Expectation. And then the second term is the expected total reward that we got through this whole learning process, right? And we wanted the difference between these two to grow sublinearly. In other words, we want to limit T approach to regret capital T over T equal to 0. Right, so this means that in the long run, in average, we are almost doing as good as the best arm, right? No difference in average in the long run. Okay, so this is the setting. And then we talked about this very simple algorithm, right? So an algorithm that has two phases. The first phase, just do exploration, and the second phase, just commit to the best arm that we believe we have so far. So the first phase is very simple. Loop over all actions, loop over all arms. For each arm, K, let's just pull it n times. Right? And then we observe, n ID reward sample from that arm's distribution. Right? And if we have n observations for that particular arm, just calculate the arm's empirical mean, right? So mu hat K, the average mean of that arm K is just a straight average over these n examples, right? N rewards. And we know that mu K is going to approach to mu K as n approach to inf, right? So this is by row of large number. And then for all the future rounds, let's just commit to the best empirical arm, right? The arm whose empirical mean is the highest. Right? So at this stage, let's just trust our estimation, right? And if as we assume our estimation is correct, then let's just pick the arm that has the highest, empirical mean at this stage, and we commit to that. So what we talked about is that we can tune that parameter n. We can control, how many rounds we want to spend on exploration, right? So that the regret of the whole learning process is balanced in the sense that it grows sublinearly, right? T to the 2 over 3. And in other words, or capital T is T, right, which goes to 0 as T approach to infinite. So we achieved our goal by just using this very simple algorithm. Okay, good. So the question for today is that can we design an algorithm that achieves this much faster regret, right? So the previous algorithm has T to the power of 2 over 3. It's okay, but it's kind of slow. Can we get, this square root T regret? So I want to emphasize that this is the optimal regret that you could get. Right? So you cannot get anything faster than that, right? No matter what algorithm. So this is a strict lower bound. Like there exists in this world, there exists no algorithm that can achieve regret that is smaller than square root of t. Right? When I say there's no algorithm, meaning there's no existing algorithm and there won't be any future algorithm, because this is a algorithm independent lower bound. So this is kind of interesting, right? So we can prove those kind of algorithm independent lower bound and saying that, hey, there exists no algorithm in this world will actually break that lower bound. This is, a hard lower bound. So let's see if we can design a very simple algorithm, achieve this optimal regret, right? And then, based on the lower bound information, we know that our job is done, right? We solve this problem pretty much optimally. The problem should be like, we should claim that the problem is solved, right? Okay, so the outline of today is, let's just study the algorithm, which is called up confidence bound algorithm. So in short, this is called UCB. And then let's just quickly analyze the performance of the UCB algorithm. Right? Any questions so far? Okay, so let's jump into the algorithm. All right, so the algorithm again, runs in this iterative interactive fashion. So now let's see that algorithm gonna maintain some statistics during the learning process. So let's see at the beginning of iteration t, for all arm I from 1 to k, let's maintain a number which is the number of times that we have tried that arm I so far. Right? So I'm just going to use this notation. So this says that from iteration 0 to t minus 1, in that period, how many times I've already tried this arm I? Right? So I'm just scanning every iteration, and I'm checking if that iteration I put in an arm that is equal to I. If it is, I just add 1. Otherwise, I just skip that step, right? So this is just counting. I'm counting how many times I've already tried that arm I. Right? And now let's also estimate the empirical mean of that arm so far. So this means that I'm just going to calculate an average, right? So let's just look at the time step where we put arm I. Let's just sum these rewards together and divide by the number of times that we have tried that arm, right? So that should be our average. So let's draw some pictures, right? So we start from t, tau equal to 0 to little t minus 1. So maybe here, every time step, maybe I'm trying 1, 1, 2, 1, 3, 3, maybe 1, so on and so forth, right? So this is the history of interactions that I have with the system, right? So I have R0, R1, R2, R3, so on and so forth, right? So all this is doing is just every iteration, let's just scan that history, right? And let's just pick, let's just check, what are the time steps that I picked up? Picked 1. Sorry about that. Right? So I'm just looking at, what are the time steps that I picked 1. So I count how many times I picked 1. That is, this particular statistics, the number of times that I put 1, right? And then on these circled time steps, these are the rewards that sampled from 1's distribution, right? And we can just sum these rewards together and take the average, right? That will be our current best estimation of the mean for arm I. Okay, so these are the two statistics that we're going to maintain throughout the whole learning process. right? How many times we have tried this arm and the current, best estimation, the empirical mean of the arm I. Right? We can repeat that, for every arm I, so that we get this pair of statistics, one for each arm I, right? Okay, so with that two statistics, we can actually do something quite interesting. So if you recall this slightly more powerful tool than this law of large number, right? This Hofstad's inequality, which tells us how far away your empirical estimation is from the ground truth mean, mu, right? In terms of the number of trials. So this is your estimated mean, right? Mu is your ground truth. Okay, so we're going to use that to build a confidence interval again, right? So remember, every round, we have already maintained two statistics, right? For each arm, the empirical mean that we can compute so far, and the number of times that we pull that arm so far, right? So which means that we can build a confidence interval for that arm, right? Using these two statistics, right? So this means that at every iteration t, right? For all arm I from 1 to k, with high probability, we can build a confidence interval for that, right? Because this is the estimated mean, right? So this is the ground truth. And this is how many times that we have already pulled arm I, right? This is like how many times of experiments that we have done on a particular arm I. So I'm just using the Hofstad's inequality here, right? So remember this magic rate 1 over square root of 1 over n, right? N is the number of experiments that we do for this particular arm. So here, every iteration t, I know that I've tried arm I n subscript ti many times, right? And I have the average mean that I computed using the history information. So let's just apply Hofstad's inequality on that I, right? On that arm I, and this is what we get. Right, so one thing that I want to mention is that here I've already applied a union bound over all iteration and over all arm I. Right, but let's not worry too much about the log terms. They're only going to affect your log terms. That is why there's a k and t. But let's not worry about that for now. Okay. And if you're interested in the details, you should go ahead and read the the material that I just posted today. Right, but let's try to get intuition about the algorithm and the intuitive analysis. Let's not worry about log terms too much. Okay. So let me just quickly summarize what we have so far. So what we stated in the previous slides is that with high probability, we have a valid confidence interval for all iteration and all arm simultaneously, right? So picture-wise, this is what we got. For all t in capital T, right, we have these confidence intervals, one per each arm. So this picture looks pretty similar to the picture that you saw from the previous lecture, right? But the difference here is that the confidence interval, they may have different lengths now, right? Because at this stage, you might try arm 1 many, many times already. That is why the confidence interval of arm 1 is much shorter than the confidence interval of arm 2, right? Because you haven't tried arm 2 too many times yet. Maybe you only tried it a few times. So you're very uncertain about the arm 2's estimation, right? And maybe, arm 3 is somewhere in the middle, right? So your confidence interval is somewhere in the middle of these two. So the picture looks very similar to the previous one, but the difference is that, the length of the confidence interval, they're going to vary over arms, right? Because we are not uniformly pulling these arms, right? One for, like n times for each arm, right? So in the previous algorithm, we just ignoring the difference between arms, let's just pull each arm n times. So that's why their confidence interval will have the same length. But here they may be different, right? maybe your algorithm tried, arm1 many, many times already at this stage. So the confidence interval will be small because we are very certain about, the estimation of arm1's mean. Okay, so that's the picture that we got by using this Hofding inequality and union bound. Right? Again, I wanted you to sort of feel comfortable about looking at this picture, right? The detailed analysis, let's not worry about too much at this moment. Right? So now let's see what the algorithm is doing. So the algorithm essentially uses this principle called optimism in the face of uncertainty. So what do I mean by optimism in the face of uncertainty? So more specifically, given the confidence intervals, every iteration, we're going to pick an arm that has the highest up confidence bound. Okay, so again, let's return back to this picture. So this is the information that I have at round t, right? And the algorithm says that I will pick arm2 because arm2's up confidence bound, the up confidence bound is the highest, right? So the top of the intervals, let's look at the top of the intervals. Let's pick the interval whose upper bound is the highest. So this is what this algorithm is doing. So basically what we are trying to do, right? So we have these confidence intervals that we know they are valid with high probability. Let's not worry about, small probability of some confidence interval bound fails, right? Let's just focus on, valid confidence interval. So this says that at this stage, these confidence intervals are the best estimation that I have, right? Like I know that the ground truth mu2, for instance, will fall into this confidence interval, but I don't know where mu2 would be. Maybe mu2 will be very high, right? As high as the up confidence of this interval. So maybe mu2 will be here. Who knows? I don't know that, right? I just only know that mu2 belongs to this interval, right? And similarly, maybe mu1 will be this too, and mu3 will be this too. Sorry, not this. Right? So if we are very optimistic, so let's see we are very optimistic, right? Then mu1 should be equal to the upper bound of its confidence interval. And mu2 should be equal to the upper bound of its confidence interval, because that's the maximum value that it could be, right? So let's just be very optimistic. Let's just say, our confidence interval, they happen to have this property where, the mean, the ground truth actually hits the top of the top confidence interval. That's the most optimistic thing that we could think about, right? In this case. Okay, so if that is the case, this principle kind of makes sense, right? That's just to pick an arm whose UCB up confidence bound is the highest. Because this is, the most optimistic case, right? That's the best, that's the maximum sort of reward that we could get, right? If everything, if you're very optimistic about this uncertainty. Right? So that's why we call it optimism in the face of uncertainty. When we have these uncertainties, right? The uncertainty means those confidence intervals. We only know that the ground truth falls into this confidence interval, but we don't know where it is. So let's just be optimistic. Let's just assume that the ground truth actually hits the top of the confidence interval, right? And in that case, picking an arm that has the highest up confidence bound totally makes sense, right? Okay, so let me summarize the algorithm, right? So this is a pseudocode. It's a one-line pseudocode. Right, for t from 0 to capital T minus 1, every round, let's just pick an arm that has the highest up confidence bound. Right, so this one is actually the up confidence bound of arm I. So this is the mean. This is the estimated mean. And this is, half of the length of confidence interval. All right, so picture-wise, in this picture, we're just picking this one, right? IT equals to 2. That is the algorithm. It's very simple. You know, all you need is just maintain 2 statistics, right? The mean and the counts. So intuitively, we could also try to understand this additional part as this rewarded bonus, right? So the rewarded bonus will be big. The rewarded bonus will be large if NTI is small, right? So if we have not tried that arm many times, let's give it a large reward bonus, right? And if we have tried that arm many, many times, let's give it a tiny reward bonus. So that's what we are trying to do, right? So the reason that we give it a large reward bonus for those arms that we haven't tried that many times, because we want to do exploration, right? Maybe next round, you know, by adding this large reward bonus, we're going to pick that arm, right? And for arms that have been explored many, many times, yeah, we don't need to add too big a reward bonus, right? The reward bonus should automatically decay with respect to the number of times that we have tried it. Right? Intuitively, you can think about this as some sort of added, like, additional reward bonus that you add so that you incentivize the algorithm to do some exploration. Right? So this idea will be very useful even in reinforcement learning. So imagine you're doing some exploration in the maze, right? You can maintain counts on the states that you visited so far, right? Add a huge reward bonus on those states where you haven't explored yet. So that incentivizes the reinforcement learning algorithm to explore those states, right?
So just to clarify, in the first step, like all the counts are going to be 0. So does that mean that all the values are going to be like positive infinity so that each one is equally likely in the beginning?
Yeah, it's a very good question. So I ignored that details. So let's see that for the first K rounds, let's pull each arm once.
I see.
Okay, because that regret of that additional step is constant K, right? Which will be fine afterwards.
Makes sense.
Yeah. So let me repeat this question. This is a good question. I purposely ignored that in this lecture, but you will see it in the algorithm pseudocode in the reading material. All right. So this n. So this is a very good question, right? So this n at the very beginning could be 0. Like, what the hell this algorithm is doing, right? Like, you put a 0 in the denominator. This is not going to work. So an easy way to fix that is that for the first K rounds, K iterations, let's pull each arm once. Okay, so now our denominator always starts from 1, right? Because we have already tried each arm once already. And the total regret of this process, this additional step, is at the most K minus 1, right? Because we tried each arm once, so the total regret is K minus 1. So this is a constant. You know, when we average everything together, K over capital T is going to approach to 0 anyway. So this step is fine. It's not going to contribute anything significant on the final regret, right? So if you do this step, then we get rid of the problem of, you know, dividing 0. Right? So maybe let's say this is our warm start. And we run our algorithm, right? So let's you know, so that we don't have to worry about, you know, a 0 in the denominator case. Okay, so yeah, go ahead.
So this could be a problem if n is like less than k, right? So I guess you'd have to maybe do a different algorithm in that case.
Yeah, so let's not worry about, you know, small capital T cases. So let's always assume that the number of rounds K is bigger than T is bigger than K. right? So this is the regime that we care, right? We care about t approach to infinite. And then in average, can we do as good as the best arm?
Hey, Professor. So like in our carpool example, like the state of the carpool is actually a continuous variable. You have 4 continuous variables. So like in those cases where the state, like they're all continuous, how would you sort of discretize or like how do you apply this UCB algorithm?
Yeah, so this is a very good question. So we will talk about that in probably next week. But the short answer is that it depends on how you, so one classical way people do is they discretize the state space, and then you maintain count on the grid. Right, so this is one approach. There's some other approach, if you start using function approximation, but we will briefly talk about that in next week. Okay, so that's the end of the algorithm. It's a very simple, one-line algorithm, right? Any questions about the algorithm? Okay, so the difference between this algorithm and the explore and the commit, right, is that like we're sort of automatically adjusting how much bonus that we should add, right, based on how many times that we have tried. And in the explore and commit phase, we will say like, regardless of what, let's just explore that arm n many times, right? So here you're sort of automatically adjusting, the incentive that you add on this arm based on how many times it has been explored, right? So you will see that this actually gives us a huge benefit when we calculate the regret. Yes, question.
Yeah. So it makes sense that this algorithm is encouraging that exploration by tuning that bonus reward. But I was just thinking, so like if we do kind of the opposite thing where we pick the arm with the greatest lower bound, that would encourage the opposite, right? Like to exploit like a particular arm.
Yeah. So very good question. Yes. So people always ask me like why we can do LCB, lower confidence bound, right? So hold this question maybe for 5 minutes.
Okay, because I was gonna ask what we like. It makes sense to do this upper confidence bound at the beginning when you're exploring, but then if you switch to an LCB, then you can exploit that one arm more and more.
Yeah. So the benefit of this, the key advantage of this algorithm is that you don't have to switch. The bonus decides that for you, right? So at the point where you have already explored it many times, like you're just using the mean, right, at this stage, because the bonus is small, right? So you never want to set a hard threshold saying that, hey, you should stop exploring.
Yeah.
Right. So like everything should be automatic here. Like you don't need to worry about tuning that threshold anymore, right? So this is just like magic. Like it does this for you. Okay, so let's see how we can analyze this approach, right? So what I'm going to do is that I will skip some very detailed step for calculating the regret of this algorithm. But let's see if we can, trying to understand the analysis from a high level. Okay, so the intuitive explanation of UCB. So let's look at this case, right? So let's see at some iteration t, this is the confidence interval that we are facing, right? And we know that the algorithm is going to pick it equal to 2. So this is the case, right? So let me ask you this question. Like, why the up confidence bound of arm2 is so high at this stage, right? In this example.
The count is small?
Yes, you're right. Yeah. So you see that the reason in this case, right? The reason that the up confidence bound, this red dot is so high, is because the length of this confidence interval is large, right? Which means that NT2 is small, right? We have a huge bonus on this arm at this moment, which means that we haven't explored that arm that many times, right? Otherwise, the confidence interval would be small, right? So in this case, we get into this situation where we picked an arm that is currently underexplored, right? The arm has huge uncertainty. That is why its up confidence bound is so high, higher than any other up confidence bound, right? So this is great. This is not a bad news, right? So this means that we are actually doing exploration. We actually identified an arm that is currently underexplored, and we try it at this round, right? So we're going to shrink the confidence interval a little bit more, right? So the algorithm automatically does this exploration for us. Okay, so this is case one. Now you will see that this is good, but I don't want to keep doing exploration, right? Because that's just going to hurt my final regret, right? So this mu2 is not a good arm at this stage. So if I keep doing that, that seems bad. Is there a way that I can, stop exploring and start committing or start exploiting? So this is this case. So now I'm showing you a different picture. Again, arm 2 still has the highest confidence interval. So let's say this is the picture that we run into, right? When we're running this algorithm on some multi-arm bandit at some iteration t. And the algorithm picks arm 2 in this case. Okay, so if we stare in this picture, like why at this stage we would pick arm 2? Like why arm 2 in this picture has very high up confidence bound? Like what's the reason? So from previous slides, we saw that it could happen when your confidence interval is huge, right? But this case, confidence interval is small, meaning that we have already explored that arm a reasonable amount of times. But still, the up confidence bound of this arm is pretty high. So what's the underlying, root cause for this case?
The true mean is better than the others. So
yes. Yes. So if it has low confidence, if it has low uncertainty, meaning the confidence interval is small, right? And we still pick that arm, that means that this arm is simply a very good arm at this stage, right? Because otherwise, how the hell its up confidence bound could be high if its confidence interval is small, right? So I have a very small confidence interval for this arm 2, but yet its up confidence bound is so high. That really means that the ground truth mu2 should be really high, right? All right, so this is also a great case because we're doing exploitation and we are picking an arm whose ground truth mean is pretty high, right? So case 1, we were doing exploration. Case 2, we are doing exploitation. Everything is automatic. Like the algorithm does not decide which step you do. It just automatically determines whether you do exploration and exploitation. So that's the intuition why we want to do up confidence bound, right? So if you do up confidence bound, there are roughly only 2 cases, right? The first case is that, yes, our arm might be a bad arm, but if the arm is really bad, but it has the highest up confidence bound, that only means that we haven't tried that arm many times yet, right? So its confidence interval is huge. So that is this case is talking about, right? Okay, so then now by doing this optimism in the face of uncertainty, we're doing exploration. So now this case is that another situation under which the up confidence bound would be high is that we indeed have already explored that arm many, many times, so the confidence interval is small. But it's just the mean of that arm itself is pretty high, right? The quantity that we care about is pretty high by itself. So of course, the confidence interval will be high, right? The upper confidence bound of that arm will be high. But this is a good case because this is a good arm. So if we pull this arm, we should have either 0 regret or very small regret. Right? So we're doing automatic, we're automatically doing this exploration and exploitation trade-off. And if you do LCB, you will not get to this phenomenon, right? Because like, think about, an opposite of this case too, right? An arm has a very low LCB. What does this mean? First, this means that it could be possible that the arm has high uncertainty. So you do some exploration, that is fine. But in this case too, the opposite of this case too, it says that the arm's ground truth mean could be very low, right? If you do LCB. If an arm has really, so okay, let me draw this picture. So maybe this arm, we're very certain about this additional arm, mu4 maybe. And let's see, mu4 is here. So this is the interval for mu4. And we saw that the lower confidence bound of mu4 is the lowest, right? And we have already tried arm4 many times. So that only means that the mu4 itself will be pretty low, right? Because that's how you're going to put that lower confidence bound pretty low. So this is a bad choice because we're picking the worst possible arm. So you're going to suffer a lot of regret. Right, so this is sort of the opposite reasoning of case 2. So let me just quickly summarize what we saw in the previous 2 slides. So case 1 says that the arm that we choose, IT, has large confidence interval, right? Which means that we haven't tried it many times yet, and thus it has high uncertainty. But this is a great thing because we do exploration in this case, right? We're going to try this arm in this round, and we're going to shrink the confidence interval for it, right? So this is not so bad. So case 2, which is the opposite of case 1, the arm that we picked actually has small confidence interval, meaning that we are pretty certain about its estimation, right? We have tried it many times already. Then the only reason that its UCB will be high is because its true mean is pretty high, right? Now, this is also a good thing because we're doing exploitation in this case, because the arm is ultimately a good arm, right? It's either the best arm or an arm that is very close to the best arm. That's right. So that's, the benefit that using this UCB algorithm, right? The benefit of being optimism in the face of uncertainty. So we either do an exploration or we're doing exploitation, right? So every iteration, one of the things is happening. Okay, so any questions about the intuition behind this algorithm? And the next, we're going to see some slightly more formal analysis of this intuition. And then in the end, let's come back to this intuition, see if everything makes sense.
Obviously, none of this works if the confidence bounds don't hold, right? Still, like if one of the other arms that we aren't exploiting ends up having a ground truth mean that's higher than
correct
above its confidence bound, this is not going to choose the optimal arm.
Correct.
Right?
Yeah, correct. So this is the same. So same issue will happen for the algorithm that we talked about on Tuesday. So remember what we did? We just conditional all the analysis on the fact that the confidence intervals are valid, because the probability of their failing is small, right? And when they fail, we don't care about the regret. So our statement will just say that with high probability, this is the regret you get. With the rest of small probability, yeah, we can't guarantee you anything.
Yeah, so delta has to be pretty small.
Yes, yes. But remember, the log delta only appears inside the log term, right?
Mm-hmm.
Which means that if you set delta to be like 0.001, right, log of 1 over 0.001 is roughly like a constant. I think roughly maybe 5 to 10.
Yeah.
Right. So it's a constant. Like log grows in almost like a constant, right? That's good. If you don't have a log yet, this isn't a big issue because you can't set delta to be too small, right?
Okay.
But this is a log, yeah. So log, just think about log as a constant, right? Like the growth rate of log is so small, right? You can make delta exponentially small, but you still pay like a, sort of a linear growth, right? After you apply log on 1 over delta.
Yeah.
You really can set delta to be exponentially small, right? 1e negative 9, for instance. Then log of that is roughly some constant, right? It's not too bad, yeah. Okay, so let's see if we can, do some math to formalize this intuition, right? Again, this is a very simple derivation, 3 lines at the most. Okay, so let's do some bookkeeping first. So let's denote optimal arm as I star, right? The arm that has the highest, ground truth mean. And let's recall that I subscript T is the arm that we picked. The arm that has the highest UCB, right? Okay, so what is the regret at this iteration, right? What's the regret of picking I subscript T? This is very simple, right? Regret at iteration T is just the difference between mu star and mu subscript IT, right? Okay, so let's calculate that. Let's upper bound that term. All right, so what I'm going to claim is this is true. Okay, so I purposely skipped some steps here. And let's see if we can, figure out what's going on here. Right, so let me just draw a picture here. So this is I star. This is IT. All right, so this is the picture that we have. Remember, I subscript T is the arm that has the highest up confidence bound, right? So that means that the up confidence bound of IT should be higher than the up confidence bound of the optimal arms, right? The up confidence bound of the optimal arm. So that we agree, right? Because the algorithm picks the highest up confidence bound, the arm that has the highest up confidence bound. So of course, the up confidence bound of the picked arm should be no lower than the up confidence bound of the rest arm, including the optimal arm, right? But we also know that the ground truth of mu star falls inside this interval, right? Which means the up confidence bound of the optimal arm should be bigger than the optimal arms under the underlying true mean mu star, right? So what I'm doing is UCB of IT is bigger than UCB of I star, right? So by this rule, and this is bigger than mu star, right? By the definition of UCB, by the assumption that the confidence intervals are valid. All right, so that's how we get this quantity, right? So this term is equals to this term, right? So I'm upper bounding mu star using the up confidence bound of the arm that I picked. Okay, I already asked this question. Okay, so now we can further lower bound this term, right? So we know that mu it will be bigger than mu hat tit minus square root log blah over n tit, right? Because this is my LCB. So the LCB should be lower than the ground truths, right? So just plug in that in. Now the mu subscript it will be canceled out. So this is just going to be the length of the confidence interval. Right, so what is this picture saying, right? So this picture says that this is my up confidence bound. You know, my mu might be somewhere here, right? So this is my ground truth. So what's the difference between the ground truth and the upper confidence bound? That is at most the confidence interval's length, right? Like difference between these two, right? It must be less than the confidence interval, which is 2 times this square root log, over n, right? So that's all these, two equations, two inequalities talking about. Okay, so what we did here, we upper bound the difference between mu star and the arm that we picked, right? The regret at iteration t by the confidence of the arm that we picked, by the length of the confidence interval of the arm that we picked, right? So this, again, this is the confidence interval length of arm it. So now let's think about the first case. The first case is that it is underexplored, meaning that n subscript tit is small. We haven't tried it many times yet, right? So in this case, this nt is small, meaning that this whole quantity is big, right? So if we have not tried it that many times, meaning the denominator is small, then the whole thing will be big, right? We will have a large, confidence interval. So from the regret perspective, this is not so good because the regret is big, right? So we're going to pay some regret, but we explore here, right? We just tried it at this round. So next round, we see something. If in the future we saw it again, the confidence interval is shrinked at least, right? So case one, unfortunately, we picked an arm that has super big uncertainty, but from the exploration perspective, we did some good job, right? We explored it in this round. So we tried it so that the confidence interval in the future will be shrinked a little bit. Okay, so what is case two? Case two is that this arm's uncertainty is actually small, meaning that we have already actually tried this arm reasonable amount of times. So this means this denominator is actually big, right? And this means that the whole thing is actually small. Okay, so why this is a good thing? This means that the regret is upper bounded by a small number in this case, right? So in this round, we're not paying too much in terms of a regret. So we actually did exploitation. Right? So another way you can think about this is that this inequality tells us that mu star minus mu it, right, is less than 2 times log blah over n tit, right? And we also know that this is bigger than 0 because mu star is the optimal arm, right? And this means that mu star minus mu it is less than square root of log over n tit, right? So if I've already explored it many times, meaning this quantity is small, right? So then from this deviation bound, I can see that it is a near optimal arm, right? Like the difference between mu star and mu it is small. So this is a good case because I'm doing exploitation, like I'm picking a near optimal arm, right? So I pay very little regret in this stage. right? So in other words, the gap between mu star and mu subscript IT is small in this case, if IT has already been explored many times. Right, so that matches to our intuition, right? The picture, the second case that you saw in that picture case, in that picture, where we have already explored IT many times, so the confidence interval is small, but nevertheless, the upper confidence bound of IT is still pretty high. That only could happen if IT is a reasonably good arm, right? So this is what formalized that intuition, in the sense that if you tried IT and IT happened to be an arm that has been explored many times, so that only means that the gap between mu star and mu IT is small, right? So this is the exploitation phase. Okay, so the last step is that I'm gonna skip that details. So the last step is just add, this per iteration regret across this total capital T many iterations, right? I'm just doing summation, and at the end of the day, I'm thinking this should be equality. So at the end of the day, I'm just have this term left. So I'm not gonna dive into the details of bounding this term, but the simple lemma tells you that, summation over T from 0 to capital T minus 1 of square root of 1 over n subscript T IT is upper bounded by square root of K capital T. So K is number of arms, T is the total number of iterations. All right, so if you plug in this in here, so you can find, if you're interested about this lemma, you can find the detailed iterations in the reading material. Okay, but let's just treat this as, sort of a mathematical tool, right? So this is nothing to do with bandit itself. This is more like, you're just trying to upbound this inequality, right? So we can do some, tricks to bound this in terms of this square root KT. Right, so if you plug it in, this gives us this very nice bound, right? Ignoring constant and log terms, we successfully get to this regret. With high probability, UCB gives us the following regret, which is roughly square root K capital T. So again, so this is optimal, right? There's no algorithm can achieve that, nor can you design any future algorithm that can, there's no algorithm that can be better than this, right? No, in the future, you can design an algorithm that can do better than square root KT. This is the optimal. Okay, so any questions about the brief analysis of this UCB algorithm?
I have kind of like a general question about why we use regret as a metric. Is that it's kind of like in that ad example where we care, like in the analogy to supervised learning, like we care about not only the final thing, but also like the error during training, almost like.
Yeah. So think about the ad. Think about the ad replacement or music recommendation system, right? So there is no like training and testing. There's no clear separation between training and testing, right? Because once you deploy that system online, every day you're doing an update, right? Like every day you're interacting with a user, so you're doing a testing. And then at the night of that day, you might use this new information to update your recommendation procedure, right? And tomorrow you're gonna redo it again.
Yeah, you still have to take the ad every time, yeah.
Yeah, so like what you care is that the average performance, right, from the first day that you deploy that system, maybe to the end of the first quarter, maybe, right? So yeah, so this is the difference between interactive machine learning and this supervised machine learning, right? Supervised learning says that let's collect all the data, let's just train a model, and then we just deploy it. Then our job is done, right? But this is not true in those like recommendation system that we are encountering every day, right? Like they constantly improving their their ability of recommending stuff. That's why they can actually recommending you pretty relevant stuff over and over again. Right? Sometimes it's very annoying because they keep recommending you the same stuff and you actually want to see something different. But that's why, you know, that's precisely the reason, that's precisely because they're running these kind of algorithms, right? Right. So eventually they don't do exploration anymore. They just committed to the best thing that you would like to see. Right. So yeah. You know, if you clean your web browser history, right? Like, or if you just, you know, log into YouTube without, you know, logging to your Google account, you will see widely different content, right? Because they don't know your preference. They need to start from exploration, right? So you can do this experiment, right? But if you log into YouTube with your Google account, right? So you will see that the material that they recommended, they're pretty, you know, relevant to your interests already, because they already explored on you, right? So now they're just exploiting on you.
Yeah, that makes sense.
Okay, so let me just quickly summarize what we talked about today. So it looks like we can end today's lecture early. So we talked about this algorithm UCB. So the principle that it used is this principle of optimism in the face of uncertainty, right? So picture-wise is that we have confidence interval for each arm every round, right? And we are uncertain where these green dots will be actually, right? So we know that they belong to confidence interval, but we don't know the exact location, right? Maybe the green dots will actually match to the upper confidence bound in the most ideal case, in the most optimistic case, right? So let's just pretend that we are in this very optimistic case, the most ideal case, and let's just pick the upper confidence bound, the arm that has the highest upper confidence bound, right? Because it is possible that this mu2 match to the upper confidence bound, right? We are very optimistic. And this is exactly this algorithm is doing. Right? So the analysis is really sort of trying to formalize these two cases, right? So case one is that the arm IT that we picked has high uncertainty. In this case means that we actually explored, right? So this is corresponding to this picture, right? Like mu2 is a bad arm in this case, but yet it has the highest up confidence bound. That only can mean that it has really large uncertainty at this stage, right? So that's great. We pick it an arm that has really high uncertainty at this moment. So we explored. The second case is sort of the opposite, in the sense that the arm IT that we tried, it actually has low uncertainty, right? Under this case, the only reason that its upper confidence bound could be very high is because the mean, the ground truth mean is pretty high, right? So you already pushed the whole interval pretty high, right? That's the only case that could happen. That's the only, that's the only case, you know, this could happen if the uncertainty about this arm is pretty low at this stage, right? So this is also a good case because we explored that arm, right? We saw in the picture in the previous slides and also, you know, the mathematical formulation, right? We saw that if we are in case two, then mu IT minus mu I star is actually small, right? That's what we saw in the picture, and that's what we saw in the, you know, the mathematical formulation, right? So this precisely says that yes, we're doing exploitation because we're picking a near optimal arm, right? And somehow, you know, this UCB algorithm, they automatically, you know, doing this exploration and exploitation for you. Right, so this algorithm is pretty magic, and it's very simple algorithm, one-line algorithm, and it's very simple to implement. And this principle is also very powerful. This is also, you know, the main principle people use to design exploration algorithm for reinforcement learning, right? Because how you incentivize the agent to explore those underexplored region. So you add reward bonus, you add a bunch of reward bonus to this unexplored region, right? so that your agent believes that those unexplored region has high rewards. So it will try to explore those unexplored region in the next round, right? And once you explore that region many, many times, you decay your bonus. So the algorithm will focus on to explore some other new region. And eventually, after the algorithm explored everywhere, then you're done, right? But you can imagine this is sort of different from random walk, right? Because random walk does not remember where you explored, does not incentivize to explore new region. But this approach actually incentivizes you to explore underexplored arm, right? And also, keep updating this reward bonus, right? Meaning that if an arm has already been explored, the reward bonus is small. I'm not going to incentivize you to explore that arm anymore, right? So this kind of mechanism is missing in our policy gradient algorithm, for instance, right? Like the policy gradient algorithm relies on randomness to do exploration. Like it could work for some cases, but for cases where you needed to do exploration, policy gradient gonna suffer, right?